extra practice?
Because it's right there.
Wait, why is there a shipwreck on the ceiling? And why are you trying to run and jump to get the shipwreck? Because you're not getting anywhere close.
Anywhere. Well, if a snowboarder gets higher, then it needs to go faster, right?
Yeah, but that means that your horizontal speed should affect your vertical speed. But I'm not sure if that sounds right.
There's a lot going on in this problem, and we're not going to solve this problem in just one video. But for this video, we're going to talk about vectors and scalars.
Where did he come from?
Hey, Shep, what are vectors and scalars?
Scientists like to categorize things. So scalars and vectors are just different ways to group things that have direction and from things that don't.
Oh, that sounds like the difference between speed and velocity.
Or the difference between distance and displacement.
That's correct! Scalars are things that only have a magnitude.
Whoa! Scalars only have a magnitude? Wait, what's a magnitude?
Magnitude is just a fancy term for amount.
Oh!
So the magnitude of the stuff in your pocket is about 8.
Okay. 1, 2, 3, 4, 5, 6, 7,
Those are mine.
and 8.
Correct! Scalars are things like time, distance, and speed, where they don't depend on direction.
So that means those quantities are never negative, because negative values indicate a direction. You can't have a negative speed or a negative distance.
And that brings us to vectors. Vectors are things or quantities that have both a magnitude and a direction.
Oh, I get it. So displacement is a vector because there's a difference between 4 meters above your origin and 4 meters below the origin.
Or like how velocity is negative for an object falling when we take it to be positive. It's moving in the negative direction.
But Shep, I noticed that both velocity and speed have the same symbol V. So how do I know what you're talking about, vectors or scalars?
That's a really good question. If we're talking about a vector, we put a hat over the symbol. No, not a real hat, but a hat like this. So it looks like an arrow. So for instance, if we're talking about speed, we use just V. If we're talking about velocity, then we would use V with an arrow on top, or V hat. We use arrows to represent vectors. So for instance, if we have an object that is moving in the north direction at 25 meters per second, then we would have an arrow at some given proportion pointing in the north direction. If you wanted to talk about an object that is only moving 5 meters per second, the arrow representing that object will only be 1/5 of the original length. The longer the arrow means longer the vector.
Why do we use vectors?
We use vectors to describe the behavior of objects moving in 2 or 3 dimensions. For this class, we're only going to worry about 2 dimensions.
What do you mean 2 dimensions? Isn't that kind of like old school Mario?
Yes, that's exactly what that means. So you can think of dimensions as pathways. So up and down is one pathway or dimension, and left to right is another dimension or pathway.
Well, how do we add or subtract vectors that are not on the same line?
That's a really good question. We're going to use 2 different methods. We're going to use the first method, which is known as the tip-to-tail method, and the second method, which is known as the adding by components. All right, let's do an example of adding vectors using the tail-to-tip method. So just to first kind of make things clear, let's set up a problem. Let's say I'm on a lake. Isn't that an awesome looking lake? Let's say we're looking from the top down, and so I've got this big lake, and you're on a boat. Let's say that's your awesome boat, and you're just floating around, and what we want to talk about is how fast this boat is going. So we're going to talk about velocity. Now, velocity direction matters, so therefore we can represent velocity using an arrow. How long the arrow represents how fast it's going, and depending on which way the arrow is pointing, represents the direction. So let's first say the vector A is going to be the boat. That's going to be the boat speed. That's not how I spell boat. There we go. So that's the speed of the boat. Let's say we want it to go 5 meters per second north. So the way that we're going to use the arrow to represent this is first we need to talk about the scale. The longer the vector, the longer the arrow. So let's say I'm going to set up my scale to be 1 centimeter. It's going to be equal to 1 meters per second. So what this means is for every centimeter my arrow is, that's going to be how fast, or that's going to correlate to how fast my boat is going to go. So if I want this to go 5 meters per second north, I need this to be at least 5 centimeters long. So I'm going to take my A vector, I put it up the ruler. Okay, that's about 5 centimeters. Okay, and so I'm going to take this arrow, I'm going to point it north. Boom. So my A vector is going to represent my boat, and I have that going 5 meters per second, and it just is going up. That's awesome. Cool. But now the question becomes is, well, what happens if you've got other things going on? What if not just the boat is going up, but what if the river decides to get a current? It just decides on its own that it's going to have a current. And so we're going to label our B vector the river. And let's say the river's going, I don't know, let's say 2 meters per second. So it's kind of pushing you at a general quick pace. Let's say it's going 2 meters per second north. There we go, 2 meters per second north. So once again, I'm talking about the scale. 1 centimeters is equal to 1 meters per second. So I take my B vector, okay, put it up here. Okay, that's about 3. So I need to shrink this down just a tad. Oh, I pointed it up. Is that about 2? Maybe it's a little longer than 2. Okay, that works. It's about 2, for better or worse. So its length corresponds with its magnitude, so 2 meters per second, and we also want this to be pointing up, so I'm going to take this. That B there is a little, we can straighten out the B so we can see that better. And so now I've got my river. So the question that we're about to answer or talk about is what happens when you add vector A to B. So if they're both heading north, we're going to try to find out what is my C vector, or what we're going to call this my resultant vector. Now resultant vector is just a fancy name for answer. So what is our answer? So if I add A and B using the tail to tip method, how long is C going to be, in what direction? So the way that this works using the tail to tip method is I take A and said, okay, it's pointing up, and it's going straight up, it's going north 5 meters per second, so it's 5 centimeters long. I am then going to add my B vector. So what I'm going to do is I'm going to take the tail of my second vector, or B, it's the second one in line, and I'm going to put to the tip of the first. So if I just add it there, I add those two vectors together, and that's going to give me my C vector. So then to find the length of the vector is I would line up the vector, okay, put butt to butt, and I put the tail of my C vector to the tail of my A, and I will stretch my new resultant vector up to the tip of the combined. So I've got A plus B is equal to my C, and now that's how long my C vector is. Now, you could probably guess that, okay, well, if the boat is going 5 meters per second north and the river is going 2, then logically, this needs to be going 7 meters per second. And we can check that by, okay, we're going to take this guy, this is my new vector, and I'm just going to rotate it and check its length. Hopefully, it is only, oh, it's not cooperating. Hopefully, it's 7 centimeters long. Oh, and look at that. It's about 7 centimeters long. So that shows us we have the right scale. So that is how we added A plus B. We put the tail of the first to the tip of the tail of the second to the tip of the first. We added that together, took a new arrow, drew it up, bingo bango, and now our resultant vector is C. And because it's pointing straight up at 90 degrees, calling east 0 degrees, then we can see how long my c vector is, which we will call my resultant, or I'll just call it RES, and that's 7 meters per second, and that's also north. And it's also north. Okay, cool. So that's not so bad, but what if the river isn't going north? Let's say the river is actually going south. We'll still make it simple, so we're still working in the vertical direction, but let's say now the river is going the opposite direction. This is the case of, well, what if we have A minus B? What happens if we do A minus B? So obviously C is going to be our resultant vector again, but we just have to figure out, well, how long is C this time? Before it was 7, now we're subtracting it. Now we are subtracting B. Whenever you subtract vectors, so we're subtracting the B vector, what that does is it flips the vector. So let's say I've got A and I'm subtracting B. So that means it flips. Boop. Just like that. And so the same way, I'm going to put the tip of the second, the tail of the second to the tip of the first. So instead of it pointing up, it would add, this now shows that it subtracts. So when I look at this, I need to retake my vector and I need to shrink it down, because now I need to put the tail of my first, tail of my first, to the tip of my second, and I put it up so this long. There we go. That's about good, pointing straight up. Okay, and that's not so bad. So now this is my new C vector, and you guys could probably figure it out. So, well, wait, if this is going 5 meters per second north, I'll just put N for now, and that's going 2 meters per second south, right out south. Okay, that's going 5 up, that's going 2 down, so then therefore C needs to be 3, right? And if you take your C vector and you drag it over here, let's rotate it to compare. We find, hey, look, it's 3 centimeters long. All right, let's try a more challenging problem. Let's say you have 2 different vectors and they're moving in 2 different dimensions, 2 completely different directions. So let's say your boat is going 4 meters per second at 120 degrees. So that 120 degrees is more like this way, okay. The way we figured that out is first we looked at the length, and I measured it, and it's about 4 centimeters long, because that's my scale, so it's 4 meters per second. And then I put it using the protractor at about 120 degrees. Bam. So we can see that's close to 120 degrees. Not perfect, but it'll work for this. It'll work for this example. Okay, just move it there. Okay, cool. And we also looked at the river. So the river, we called that our B vector, and that's 3.5 meters per second, and that's at 220 degrees. So if that's 180, that's 270, 120 is about there. And I went ahead and I measured it beforehand, and it's 40 degrees below, about, you can see. All right, like that. So the question is, how do we add these 2 vectors using the tail to tip method? We're going to do A plus B, and then we're going to do A minus B. So starting with A plus B, if I wanted to find my new resultant vector by using the tail to tip method, what I would do is first set up my vectors like I have them, like so. So I have the corresponding magnitudes, 4 meters per second and 3.5, at the corresponding angles. So they're all set up to go. I'm going to do A plus B. So A is set. I'm going to have it start at 0, 0 and end where it's pointing at, and its given length. And now I'm going to add B. So the same way that I did the first one, I'm going to put the tail of the second vector to the tip of the first. And then now that I have both of my vectors, I'm going to measure, what is this change? So then I put my C vector right here, and I lined it up so the tails of my first one line up and the tip of my second one line up. So this is why it's tail to tip. So I lay it here, put the tip there, And we can see, all right, depending on how long it is and what the angle is, that's what my C is going to be. So if we're going to look at C, first let's find out what is the direction, because that'll probably be the easiest thing to find first before we move it. So I take my protractor, and I set it up like so, and say, all right, I'm going to make an educated guess. That's got to be, let's say that's about 160 degrees. So I know that's 160 degrees. I'll leave it just like that. 160 degrees. Let's find out how long it is. So if I were to do that, I would take this. Okay, and that length is about, if I look very carefully, it looks to be about, let's call that 4.4 meters per second. 4.4 meters per second. And you say, well, how do you know it's 4.4 meters per second though, Shep? Well, look at my arrow. We just drew the length from here to here. So that's the resultant vector. And then we looked at the length of it. And we know that 1 centimeter is equal to 1 meter per second. So it came out to be about, I would say that's close to 4.4. because it's right below the halfway mark. So we can call that 4.4 meters per second. And it's at 160 degrees. Awesome. Now let's try A minus B. So A minus B, we're going to leave that there because it's starting and it's the correct direction. Now we talked about what do you do when you subtract a vector? Well, you just flip it. So instead of going that way, I'm just going to flip it 180 degrees. Just like that. So instead of 220 degrees, that's going to be 40 here. Oh, and boom, just like that. Good. And then I'm going to put the tail of the second to the tip of the first. There we go. All right, so that's about it. We'll call that good. We might even be able to change that just a little. So the length, we'll check that here in a second. The angle, let's call that 84 degrees. And then let's find out how long it is. So if I take the ruler, measure it this way, it's a little different. It's 5.6. 5.6 meters per second. So that's pretty neat. Okay, so we just got done doing the tail to tip method of adding vectors together. Now let's do a different way. Same problem, but now we're going to try by doing it by the components method. So what that means is we're going to take each vector and break it up into their components. And what I mean by a component is just the part. And generally for us in this class, we're going to be talking about two different components. We're going to talk about the vector in the x direction, which we know is the horizontal part or component, and then Vy, which is the vertical part or component, just like this. So if I take any vector, let's say my A vector, it has a certain amount that it's going in the x and a certain amount it's going in the y. So I set it up like this. It has it going in the x. Let's leave that blue. Let's do another arrow and see how far it goes up. So like so. So like that. Oh, let's make this a little straighter. Let's make that red. Okay, so what I'm doing here is I'm just taking each of the each vector and I'm breaking it into the two parts. It's going some in the x, it's going some in the y. And I want to find out how much in the x is it going? How much in the y is it going? I know it's going 4 meters per second at 120 degrees, but how much of that is in the west and how much is that in the north? what we're going to do is use this method of using trigonometry. So I know that this angle is what I'm looking for. It's at 120 degrees, so that means that little angle in there is 60 degrees, about. That's an ugly 60, but you get the idea. It's 60 degrees, and I want to find out what is my v of x. How much is that? So to find that out, I look at this angle, and I look at the side, and my v of x is my horizontal side. So it's my horizontal side, and it's my adjacent side. So I have my adjacent. I know my hypotenuse. My hypotenuse is 4 meters per second. And when doing problems like this, your hypotenuse is usually your vector. So it's 4 meters per second, so that's my hypotenuse, 4 meters per second. That's how fast it's going. I want to know how fast it's going in the x. That's my adjacent side, so I'm going to use the cosine of that angle is equal to the adjacent divided by my hypotenuse. My adjacent side, I'm gonna call that v of x because I don't know what that is. In fact, I'm gonna call it VAX. So that looks a little ugly, just like that. VAX, because it's my velocity of my boat, or a, in the x direction, and I'm gonna divide that by my hypotenuse, which is 4 meters per second. So now I'm looking for my opposite side, or no, I'm sorry, I'm still looking for my adjacent side. That's my VAX. I want to figure that out. So to get VX by itself, I'm going to multiply both sides by 4 meters per second. Do the left 4 meters per second. And then that will cancel out. So my VAX is going to equal 4 meters per second times the cosine of my angle. And if I take east to be 0 degrees, I can say that 120 degrees is in here. Now, if you use the whole angle, you'll see something that's cool. So, VAX is equal to 4 meters per second cosine of 120 degrees. We're taking east to be 0 degrees. That means west is 180. In this perspective, east is positive and west is negative. We talked about that in class not too long ago. So if I do 4 meters per second times cosine of 120, what should be the sign of my Vx? If it's pointing in the negative direction, then it should be negative. So let's check that out. So I pull out my calculator and say, okay, let's use the whole angle. 120 degrees to the cosine is, ooh, look at this. It is negative 0.5. Oh, that's just cosine, so let's multiply that by 4. And I get negative 2. So that means negative 2 meters per second. That's my VAX. And if you look at that, that makes sense. It's moving 2 meters per second in the x direction. It's moving west. So that makes sense for VAX. Okay, so I'm going to just write this down over here. VAX. Put the arrow on top. Minus 2 meters per second. Now, the minus 2 tells me it's in the west direction because we're taking east to be positive. Now, let's find the VAY. If I'm trying to look for my VAY, that is the opposite side of my angle right here. So the opposite, and I know my hypotenuse. I could use the tangent function and use the negative 2 meters per second if I wanted, but I'm going to stick with my VAY and my hypotenuse. My opposite and my hypotenuse, that means I'm going to use the sine of my angle is equal to VAY, velocity in the y direction of my A vector. Divided by 4 meters per second. Once again, I'm going to multiply both sides by 4. So VAY is equal to 4 meters per second times sine of 120. If I put in just 60 degrees, so I didn't show you this last time, But if, let's say, I put in 60 degrees and hit cosine, that gave me 0.5 times 4. So if I use just the simple angle, the problem is it gives me a positive 2. I know that my Vx is moving in the negative direction, so that's why when I used 120 in cosine, I got negative 2 meters per second. And that gives me the right direction. So that's why you want to use the complete angle from east, 120 degrees. You don't want to use 60, you want to use 120. So if I use 120, VAY becomes, let's do this, clear this out, 120 times sine. Okay, that looks nice and messy, times 4, gives me that. So what is that? That is 3.4. Let's round it and be nice. It's 3.5 meters per second. Okay, so I only got one sig fig there. Okay, now I got 2. So VAY equals to positive 3.5 meters per second. Okay, so now I've broken my A vector into 2 components, VAX, VAY. I need to do the same thing with my B. Okay, so I went ahead and did that off camera. So to find my VBX, I did 3.5 times cosine of 220 to get me a negative 2.7. And did VBY, I did 3.5 times sine of 220. So what this is, remember, this is my hypotenuse. That's how fast they're moving. That in total, 3.5 is the total magnitude. And this is the angle that they're pointing at. So if I look at my B vector, it's moving in the negative x, negative y direction. So both of these answers make sense. So now that I have both my A and B vectors and the broken up into components or parts, so both horizontal and vertical, I'm now going to add them and subtract them together. So let me do A plus B. So to find my C, the C component, actually let's find VCX. So in the x direction, my new C vector is going to be the amount in my x for both A and B. So I'm going to take my x component of my A, my x component of my B, and I'm going to add those two together. So if I take A plus B, that's going to give me somewhere over here. So that means I have VAX is negative 2 meters per second plus negative 2.7 meters per second, and that gives me a whopping negative 4.7 meters per second. Now, that is in the x direction, so that's pointing all west. If I wanted to find my new component in the y direction, that would be VAY plus BY. VAY is 3.5 meters per second, and that's going to add to negative 2.2 meters per second, and that gives me, what does that give me? A positive 1.3 meters per second. So, we're not quite yet done. Almost, though. Almost. So, now we have my new resultant vector broken up into components. I know that in the x direction, let me take a new arrow. In the x direction, it's going 4.7 meters per second x. So, let me call that, we'll call that my blue. I'll make it look a little bigger. And that's going 4.7, so I need this to be a little shorter. 4.7 is about there. It's a rough estimate, so we'll just keep it that. That's what my x component is doing. In the y, it's doing negative 1.3. So let me just draw it here. Negative 1.3, close to be there. Make it a little bigger. Okay. And this needs to be, if I kept that all the same. So if I've got my, let's make that blue. Okay, so my x is negative 4.7. So I measured it out to be 4.7 centimeters, 1.3 meters per second. It's going south. Or is that north? Oh, I'm sorry, that's north. So this guy was right. Just put them right side up. It's still heading in the north direction. So then now, to find my C, I've got to figure out a way of how am I going to put, oh, I keep changing this. I got to figure out a way to find my C length. I know the length of my A. I know the length of my B. So I know A is negative 4.7 meters per second. I know this is a whopping 1.3 meters per second. So how would I find C? If I know A and B, oh, this reminds me of my good pal Pythagoras from kicking back in the days. And we're going to use the Pythagorean Theorem to find what C is. So if we use C is equal to the square root of my A, let's call that negative 4.7 meters per second squared, we're going to add that to 1.3 meters per second. This will give me my C value of how long my magnitude is. And let me do this real quick. Squared plus 1.3 squared. Okay, so that gives me about it's about 4.8 meters per second. That's the length. So if I compare it with my tip to tail method, A plus me gave me 4.4. That's 4.8. That's not bad. This is more accurate because we correctly broke this up into components, whereas using the tail to tip method, it's a little bit more unclear just because of the uncertainty of the ruler and the protractor and using it on a computer. But you can see that, hey, they closely line up. Okay, so that's 4.8 meters per second. But how do I find the direction? So the big thing is I'm looking for that angle, right? So how would I find the angle if I know the opposite side and the adjacent side? If you're thinking, well, wait, can't I use just the inverse tangent of my y over x? You're correct, just like we did in class, or hopefully did in class. So if I do this is 4.7. This is getting a little messy, but if I do the inverse tangent of 1.3 divided by negative 4.7, it gives me a whopping negative 15.5 degrees. Let's make sense of that. What is that? So actually, let me move this down. So if I've got a negative 15.5 degrees, I know my x is in the negative spot. I know my y is in the positive. So if east is equal to 0 and I just look at this negative 15, that makes me think that it's down over here. But I know for a fact that my new vector is up here by looking at the x and the y. I have a negative x, positive y. That puts me in this the second quadrant right here. But negative 15.5 tells me that it's somewhere down here. And that doesn't make any sense. So to correct this, it's just 180 degrees off. So you add 180, and you get about 164.5 degrees. So we can say that 164, if we compare, hey, not bad, 160 degrees. They both line up pretty well. One is using the tip-to-tail method or the tail-to-tip method by drawing out the vectors, and the other one is breaking them components using trig. This is really messy. Make sure you go back and re-watch the video. But this is the general method of using the tip-to-tail method and the adding by components.
Wait, where's Deshaun?
I think he's still in the hallway.